Welcome to part 6 of this week's online lecture. In part 6 we will discuss the fine structure associated with the diatomic vibrating rotor. This is a typical potential energy surface for a diatomic molecule. The potential energy is plotted as a function of bond length. The potential energy surface is literally the surface upon which our nuclei are able to move. And the two motions we are interested in are vibration and rotation. They rotate and vibrate within this potential energy surface. The difference in energy between the bottom of the potential energy well and the dissociation limit is the dissociation energy from the bottom of the potential energy well and is labelled dE. The solid lines here identify vibrational energy levels for V equals 0, V equals 1 and V equals 2. The vibrational energy levels allow me to define D0, which is the dissociation energy from the V equals 0 level. So the dissociation energy is labelled with the subscript to indicate the starting point for dissociation, and E subscript indicates the equilibrium position at the bottom of the potential energy well, and a number subscript indicates the particular vibrational level from which the dissociation happens. Most frequently, of course, we are going to discuss dissociation from the vibrational ground state, and so that would be D0. But potentially I might be interested in dissociation from the V equals 1 state, and in which case we could label that D1. Here I've drawn some further energy levels towards the bottom of the potential energy well. These levels have the same amount of vibrational energy. They are all defined by the quantum number V equals 0. But they have different rotational energies. They have different values of J. Molecules in the energy level identified by the solid line associated with V equals 0 have the vibrational energy associated with V equals 0, but they also have the rotational energy associated with J equals 0. Molecules in the energy levels identified by the dashed lines also have vibrational energy associated with V equals 0, but they have rotational energy associated with J equals 1, 2, 3, etc. Molecules in these levels up here have vibrational energy associated with V equals 1, but they have different values of J. The really important thing you want to note is that we can define any of these levels, whether it is solid or dashed, by two quantum numbers. I know they are in a particular electronic state. So the electronic state is just defined by the potential function. So given this electronic state, I only need two quantum numbers to define the energy of a particular molecule, its vibrational quantum number and its rotational quantum number. Because once I've got these two numbers, I know how much rotational energy it has and I know how much vibrational energy it has. And if I want to know its total energy, I can just sum it together. And that's the basis of spectroscopy. Once I know the energies of any levels and I've got my selection rules which tell me how I can change my V or J quantum numbers, I can say what transitions are allowed in my system and I can predict the spectrum. Between the bottom of the potential energy well and the state identified by V equals 0 and J equals 0, we have our 0 point energy, which means that I can write dE in terms of D0. dE will be equal to D0 plus our 0 point energy. And the 0 point energy is just the energy of our V equals 0 state. That is a half nu E minus a quarter nu E chi E. So when we excite a molecule from one vibrational state to another, we predict there will also be a change in the rotational state. The molecule will be either rotationally excited or de-excited during the rho vibrational transition. I've drawn out the potential energy again, but I want to focus on the V equals 0 and V equals 1 states and expand it. This is the energy level diagram again, and I've written this zigzag here to illustrate the big gap in energy between the levels associated with V equals 0 and those associated with V equals 1. All of the levels identified with the V equals 0 quantum number have exactly the same amount of vibrational energy, that is, a half nu E minus a quarter nu E chi E. and all of the levels identified with the v equals 1 quantum number have exactly the same amount of vibrational energy. That is 3/2 nu e minus 9/4 nu e chi e. Both of the energy levels labelled by J equals 2 here are pretty much the same rotational energy. The reason why it's not exactly the same is because as you go to higher and higher vibrational energy levels, the bond length is going to change slightly because of anharmonicity. And because the bond length changes, it means the rotational constant does change a little bit. Remember, the rotational energy is going to be proportional to the rotational constant. So it's not quite the same rotational energy, but is almost the same. The bottom line is, if I know V and I know J, and although there is a little bit of coupling between the two, in the way I've just described, I can determine exactly what the energies are for all of these energy levels. Now, when I excite a molecule from an energy level associated with V equals 0 to one associated with V equals 1, it can either increase its rotational energy or decrease its rotational energy. We can either excite it or de-excite its rotational energy when we vibrationally excite the molecule. I've tried to illustrate the Boltzmann distribution we expect for our molecules in the V equals 0 energy levels. Notice that I've put more molecules in the J equals 1 state than the J equals 0 state because remember, rotational levels are degenerate. The level of degeneracy increases as 2J plus 1, and as I've stated before, the more levels you've got with a particular energy, the more chance you've got to have molecules in those levels. At thermal equilibrium, this may well be the kind of population in each of the rotational levels associated with V equals 0. It is clear that during a vibrational transition, we are going to have transitions from a large number of initial J states. The Born-Oppenheimer approximation is something you may have heard of before. This is a way of separating the electronic energy from the vibrational and rotational energies. Imagine that I stretched the bond of a molecule. What happens to the electrons? Do they stay where they originally were, or do they move? Because of the difference in energies and the difference in mass of the electrons and the nuclei, what happens is that the electrons change instantaneously compared to the speed with which the nuclei are moving. They adjust themselves instantaneously. It enables us to discuss vibration and rotation independently to the electrons themselves. So we can just consider the molecule rotating and vibrating in the potential energy well. We can assume that the potential energy well doesn't adjust because of the vibrations and rotations, and it is an incredibly good approximation. Further, because of the differences in energies, we can largely separate the vibrational energy away from the rotational energy, and just consider the total vibrational energy as the sum of the vibrational energy and the rotational energy that we would calculate from the vibrational problem and rotational problem separately. Now, although I have already mentioned that there is some coupling between the vibrations and rotations, let's start by considering them to be independent. So we will ignore centrifugal distortion to reduce the amount of mass. We can always include it later. If I want to know the energy of a molecule that is in the V vibrational state and the J rotational state, it literally is just the vibrational energy plus the rotational energy. And I can write out our vibrational term and rotational terms like so that the total energy, or rho vibrational energy, is going to be V plus a half nu E minus V plus a half all squared nu E chi E plus B times J into J plus 1. The total energy is just the sum of the vibrational energy and the rotational energy. To predict the spectrum that will result from rho vibrational transitions, we need to take into account both the selection rules, that delta V can be plus or minus 1 or plus or minus 2, etc. But of course, transitions for delta V greater than plus or minus 1 will exhibit far weaker spectral line intensities, and that delta J is equal to plus or minus 1. Well, let's see how that will affect things. Let's draw out our row vibrational energy levels once more. We're going to look at just the fundamental band in which we excite molecules from V equals 0 to V equals 1. But delta J has to be equal to plus or minus 1. What will this mean? It will mean that I can get transitions like this, from J equals 0 to J equals 1, or J equals 1 to J equals 2, or J equals 2 to J equals 3, or J equals 3 to J equals 4. Or I can get transitions like this, from J equals 1 to J equals 0, J equals 2 to J equals 1, J equals 3 to J equals 2, and J equals 4 to J equals 3, and so on. So I can have these blue transitions where J is increased by plus 1, and I can have these red transitions where J has decreased by 1. When J has increased by 1, we identify these transitions as R-branch transitions. Notice that all of these transitions where J has increased will be at a frequency that is larger than the fundamental frequency. The fundamental frequency can be identified in the hypothetical transition in which J doesn't change. When J has decreased by 1, we identify these transitions as P-branch transitions. Notice that all these transitions where J has decreased will be at a frequency that is smaller than the fundamental frequency. Let's use our knowledge of the vibrational and rotational energies and the selection rules to predict transitions in the P branch, where J decreases by 1, and in the R branch, where J increases by 1. So for the P branch, the rotational state changes from J double prime to J prime. The double prime indicates the initial state, and the single prime indicates the final state. This is purely a convention. So if my initial state is J double prime, then my final state is related to my initial state because J prime will be equal to J double prime minus 1. Remember, this is for the P branch transition. The rotational state has decreased by 1. So if my initial state is J double prime, then my final state is related to my initial state because J prime will be equal to J double prime minus 1. The rotational state has decreased by 1, which is the definition of a P-branch transition. This means that I can write down the frequency of any line in the P-branch. Here is the total row vibrational energy of the final energy level. And here is the total row vibrational energy of the initial energy level, which I'm subtracting to find the difference, which will be the frequency of the spectral line. Now I can rearrange this equation here and substitute for J double prime with J prime plus 1, which is the relationship for the initial and final rotational states for a P-branch transition. Therefore, I can substitute for J double prime in the rotational term for the initial state with J prime plus 1. The result is B into J prime plus 1 into J prime plus 2. So you just simply substitute into this equation and you get this. We can now simplify this expression, and this is what you get. B times J prime into J prime plus 1 minus B into J prime plus 1 into J prime plus 2 will just be 2B into J prime plus 1. So we have our fundamental frequency, which is nu0, minus the result from the difference in the rotational energies, which is minus 2b into J prime plus 1. We can do exactly the same for the R branch. In the R branch I go from J double prime to J prime again, but I can write J prime in terms of J double prime because for the R branch J goes up by 1. So therefore J prime must be equal to J double prime plus 1. Once again, I can write down the frequency of a transition in the R branch as a difference between the row vibrational energy in the final state and the row vibrational energy in the initial state. This time I will substitute for J prime, so I substitute in J double prime plus 1 into this equation. And therefore I get an expression that looks like this. it will be nu0 again, because this is my fundamental frequency, plus the term 2b into j double prime plus 1. So there are two differences here between the P and R branch lines. In the P branch, the difference between the rotational energies is negative, but in the R branch it is positive. In the P branch I define it in terms of J prime, the final J value, and in the R branch in terms of J double prime. This is solely to show the similarity between the expressions. Note that we never get a transition at exactly the fundamental frequency. These two equations define all the possible spectral lines, the P branch and R branch. There are no other branches for the diatomic. For the P branch, the minimum value of J prime is 0. It cannot go below 0. You can go from a J equals 1 to a J equals 0 state. So the minimum value of J prime is 0. And you substitute this into the equation, and the first line in the P branch will therefore be at nu0 minus 2b. Again, the minimum value of J double prime is 0 as well, and so therefore the first line in the R branch will be at nu0 plus 2b. This means there's going to be a gap of 4b between the first line in the R branch and the first line in the P branch. And in the middle of that gap is going to be the fundamental frequency. So this enables us to easily identify which is the first line in the P branch and which is the first line in the R branch, because all we need to do is find that gap. Once we've found that gap, we know that lines at smaller frequencies are P branch lines and lines at higher frequencies are R branch lines. Note that the centre of this gap associated with nu0 is referred to as the band origin or band centre. So we've got two sets of rotational fine structure on either side of the band origin, exactly what we saw with the carbon monoxide spectra. And notice that I can also write the P branch in terms of J prime or J double prime. And here is the expression once again for the R branch. So these are the transitions that we've seen. We've got the R branch over here, and we've got the P branch over here. So now that we know what the frequencies are for the P branch and R branch spectral lines, we can predict the structure of the rho vibrational spectrum. Here is the rho vibrational spectrum predicted by our expressions for the spectral line frequencies for transitions in the P and R branches. Note the gap I spoke about, which occurs at the fundamental frequency. The first line at higher frequencies is part of the R branch, and we identify it as R0 because it is associated with the J equals 0 to J equals 1 transition. And the first line in the P branch at lower frequencies is labelled P1 because it is going from the J equals 1 level to the J equals 0 level. The number refers to the initial level. This type of convention is consistent throughout spectroscopy. The numbers that we generally use when we try to label a spectral line refer to the initial state. The line labelled R0 is for the transition from J equals 0 to J equals 1, and the line labelled R1 is for the transition from J equals 1 to J equals 2, etc. Similarly, in the P branch, the line labelled P1 is for the transition from J equals 1 to J equals 0, and the line labelled P2 is for the transition from J equals 2 to J equals 1, etc. The number identifies the initial rotational level. We can also see that in this analysis, where we've ignored centrifugal distortion, the spectral lines are evenly spaced. And you can see that the difference between two adjacent spectral lines, ignoring the gap at the band origin, is just going to be 2b. So this explains the vibrational spectra of carbon monoxide that I introduced in part 1. We've now accounted for both observation 3 and observation 4. With observation 3, the low resolution averages out the fine rotational structure, so that we only see two broad bands associated with the unresolved P and R branch spectral lines. But at high resolution we can see the rotational structure, and we can see the fact that these are evenly spaced as predicted earlier. So you can see here the R0, R1, R2, R3 and R4 spectral lines. Similarly, the P1, P2, P3, etc. So you can see how easy it is to label our lines. You just find the band center. The first line at lower frequency is P1 and the first line at higher frequency is R0. You can know exactly what the J quantum numbers of all the lines are. I just want to emphasize this once more. The picture that I am trying to imprint in your mind is this idea that the quantum mechanics gives us two things. It enables us to define a level with quantum numbers, and if I know the quantum numbers associated with our levels, I can determine its energy. The other thing that quantum mechanics tells us is the selection rules, and if I know the selection rules, I know which transitions between energy levels are allowed. Once I have that information, I can predict any spectrum. This is the end of part 6 of this week's online lecture. Please continue on to part 7.